The sun has been especially strong of late, and it will go through a crucial and captivating change: the inversion of its alluring field. This plug occurs generally at standard ranges, meaning the midpoint of the solar cycle, and it has expansive ramifications for us here on Earth. Truth be told, it's conceivable that quickly the sun could address a serious danger that could accomplish complete turmoil and fiasco for everybody in the world. As you will find, the sun's attractive field is made by the headway of electrically charged gases in its inside, a cycle known as the solar dynamo. Over the long haul, this attractive field turns out to be powerfully marvelous and reshaped because of the sun's change and convective advancements. In the end, this cycle prompts a total inversion of the attractive limit. The north attractive pole changes into the south attractive pole and vice versa. So, might we at any point break down the entire cycle and take a more concentrated gander at the sun? The sun is made basically out of hydrogen and helium as plasma, a state of matter where electrons are not bound to particles, bringing about a blend of free electrons and particles. The sun's inside is isolated into several layers, with the center at the center encased by the radiative zone and the convective zone. The center is the sun's most significant locale, where nuclear fusion occurs, changing over hydrogen into helium and conveying titanic measures of energy. Over the center lies the radiative zone, where energy is moved outward through radiation. In this space, energy moves bit by bit outward as photons are absorbed and re-emitted by the solar plasma. The outer layer of the sun's inside is the convective zone, where energy is moved by convection. Hot plasma ascends towards the surface, cools, and then sinks down, creating convective streams. The solar dynamo process works fundamentally in the convective zone and the tachocline, a slim layer that lies between the radiative zone and the convective zone. The tachocline is critical since it's where the sun's differential rotation and shear flows assume a vital part in producing the attractive field. Now, here's something interesting that you likely won't have heard. The sun doesn't turn as a solid body. Rather, various parts of the sun pivot at different rates, with the equator turning faster than the poles, an eccentricity known as differential rotation. This differential rotation stretches and winds the attractive field lines, expanding the attractive field. The solar cycle is an around 11-year cycle during which the sun's attractive field goes through a series of changes, finishing in an inversion of its furthest point. This cycle is driven by the solar dynamo and incorporates several phases. Close to the start of the solar cycle, the sun is in a condition of solar minimum, characterized by a low number of sunspots and minimal solar activity. The attractive field is generally clear and bipolar, with a distinctive north and south attractive pole. As the cycle progresses, the number of sunspots increases. Sunspots are locales of intense attractive movement and are related to the rise of attractive motion from the sun's inside. These sunspots show up 2 by 2 with inverse attractive limits and relocate towards the equator over time. Around the midpoint of the solar cycle, the sun arrives at solar maximum, a period of peak activity with the largest number of sunspots, solar flares, and coronal mass ejections, CMEs. The attractive field turns out to be incredibly complex and tangled because of the constant twisting and shearing by differential rotation and convection. As solar maximum fades, the attractive field begins to reconfigure itself. The contorted and tangled attractive field lines reconnect, and the global attractive field gradually switches its limits. The north attractive pole turns into the south attractive pole, and vice versa. This cycle is facilitated by the advancement and restructuring of attractive motion areas. After the limit inversion, the sun enters a time of declining activity, returning to solar minimum. By and by, the attractive field reconfigures, and the cycle is prepared to begin anew. Currently, we're in the solar maximum stage, and the sun's attractive field is about to flip. During this stage, we can hope to see some sensational action from the sun that could be as hazardous as it is captivating. However, the sun's attractive field inversion is definitely not a surprising flip, but instead a continuous cycle. As the solar cycle progresses, the sun's attractive field goes through a progression of changes. At the point when the attractive field is at its most twisted and tangled state, it reaches a tipping point and begins to redesign itself, bringing about a flip. So, do we have any idea when the sun's attractive field will invert? Researchers monitor the sun's attractive activity, utilizing a variety of instruments and strategies. Observatories equipped with strong telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the sun's attractive field and its changes over time. One key marker of a coming attractive inversion is the behavior of sunspots. During solar maximum, sunspots appear more frequently and are more pronounced as they move towards the sun's equator, a signal that the attractive field is becoming more unstable and is preparing to flip. While we're on the topic, we should dive a bit deeper into sunspots. When the sun's attractive field lines become wound and tangled because of differential rotation, the sun's equator pivots quicker than its poles, causing the attractive lines to stretch and curve. When these lines circle over the sun's surface, they repress the convective progression of hot plasma from the sun's inside, resulting in the cooler, more obscure patches seen in sunspot images. Sunspots are not just fascinating solar features. They can sometimes produce very strong solar flares and coronal mass ejections, CMEs. These phenomena release gigantic measures of energy and charged particles into space. When directed towards Earth, they can disrupt satellite communications, influence power networks, and present dangers to astronauts in space. Additionally, increased solar activity can enhance auroras, but also raise radiation levels in Earth's upper atmosphere. So while we're on the topic, let's examine the difference between solar flares and coronal mass ejections. While both are extraordinary outflows of energy from the sun, they differ significantly. Solar flares are abrupt, intense explosions of radiation brought about by the release of attractive energy associated with sunspots. They release a lot of energy and light, often as X-rays and ultraviolet radiation. Consider them a blaze of brilliant light and heat on the sun's surface, like a massive explosion. Conversely, CMEs are huge ejections of solar wind and attractive fields from the solar corona. They can be thought of as giant bubbles of gas and attractive fields ousted into space. When a coronal mass ejection happens, it sends billions of tons of solar particles into space at exceptionally high speeds. So while solar flares and CMEs are connected, they are not the same. A solar flare can occur independently, but sometimes an especially impressive solar flare can be accompanied by a CME. While a solar flare doesn't necessarily cause a CME, they can be related in terms of danger. It depends on what we're talking about. Solar flares can disrupt radio communications, navigation signals, and pose a significant risk to astronauts in space due to the intense radiation. CMEs, however, can have a more far-reaching impact. They can cause geomagnetic storms that disrupt power systems, satellite operations, and those delightful auroras. They can also increase radiation in Earth's atmosphere. While solar flares are intense and potentially destructive, CMEs tend to be more perilous on a broader scale due to their ability to influence Earth's attractive field and thus pose a serious threat to Earth's technology and infrastructure. Another consideration is that during times of high solar activity, the amount of high radiation reaching Earth also increases. Satellites and other space vehicles are especially vulnerable to elevated solar activity. The charged particles from the sun can damage electronic components, disrupt communication signals, and even alter satellite orbits. Besides causing damage to technology and infrastructure, what else can happen to the planet? While the sun's attractive field inversion doesn't directly influence Earth's climate, the related changes in solar activity can have an effect. Some studies suggest that variations in solar radiation can impact climatic conditions and weather patterns. For example, increased solar activity can lead to a slight warming of Earth's atmosphere, which could fuel existing climate change. Might it be said that auroras are the only positive aspect we experience here on Earth? Conceivably, one of the most noteworthy impacts of increased solar activity is the enhancement of these staggering lights. These natural light shows, known as the northern and southern lights, happen when charged particles from the sun interact with Earth's attractive field and atmosphere. We hear a lot about the aurora borealis. However, these lights can also be seen around the South Pole. During times of high solar activity, auroras become more frequent and can be visible at lower latitudes, providing dramatic evening displays. However, aside from the lovely auroras, there are also concerning aspects of the sun's attractive inversion that could occur if we are not prepared. something could happen that could lead to global turmoil. One of the principal risks associated with an attractive field inversion is the increased probability of geomagnetic storms. These storms occur when solar wind, weighed down with charged particles, interacts with Earth's attractive field. In extreme cases, they can cause widespread power outages and damage infrastructure. One such event occurred on the morning of September 1, 1859. Astronomer Richard Carrington was observing the sun through his telescope, as he had done many times before. However, what he saw on this specific day would stand out forever as the first recorded solar storm. At 11:18 a.m., Carrington saw a brilliant flare of white light radiating from a group of sunspots. This event, now known as the Carrington event, marked the beginning of the largest geomagnetic storm ever recorded. The white light Carrington saw was a gigantic solar flare, an intense explosion of radiation caused by the release of attractive energy stored in the sun's environment. This flare was so strong that it produced a tremendous coronal mass ejection, CME, directed towards Earth, traveling at an astounding rate of more than 4 million miles per hour. The CME reached Earth in just 17.6 hours, a remarkably short time frame considering the sun is 93 million miles away from us. When the CME collided with Earth's magnetosphere, it triggered a geomagnetic storm of extraordinary force. The impact was immediate and far-reaching, disturbing Earth's attractive field and causing currents in the ground. Furthermore, telegraph lines, which were the foundation of global communication at the time, experienced severe disturbances. Flashes flew from telegraph machines, operators received electric shocks, and some message stations even burst into flames. At times, the induced currents were so strong that telegraph operators could send and receive messages even after disconnecting the batteries. One of the most striking and critical results of the Carrington event was the marvelous display of auroras. During the Carrington event, the auroras were so bright and ubiquitous that they were visible far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the skies illuminated with vibrant colors. The auroras were so intense that they lit up the night sky to such an extent that people in the northeastern U.S. could read newspapers by their light. In the Rocky Mountains, gold miners were allegedly roused by the brilliance, mistaking it for dawn and beginning to prepare breakfast. People described the sky as having shimmering red, green, and purple hues moving and glowing across the horizon. Now, imagine if a solar storm of the magnitude of the Carrington event were to hit Earth today. The results would be utterly catastrophic. The sun is going through a significant change. The inversion of its attractive field, an interaction that happens roughly every 11 years as a component of the solar cycle. This event, driven by the solar dynamo, can have broad implications for Earth, potentially causing disruption and calamity. The sun's attractive field is made by the development of electrically charged gases in its interior, resulting in a complex attractive field that ultimately switches its limits. The sun is fundamentally made out of hydrogen and helium plasma, with energy produced by nuclear fusion in its core. This energy is moved outward through the radiative zone and then by convection in the outer layers. The solar dynamo system, which operates in the convective zone and the tachocline, generates the sun's attractive field. Differential rotation of the sun, where the equator turns faster than the poles, stretches and enhances attractive field lines, driving the solar cycle. Right now, the sun is in the solar maximum stage, where sunspots and solar activity are at their peak, prompting potential dangers like solar flares and CMEs that can disrupt satellite communications, power grids, and pose dangers to astronauts. Researchers monitor the sun's attractive activity and sunspot behavior to predict the timing of attractive field inversions. Sunspots, which result from tangled attractive lines, can produce solar flares and CMEs, both significant emissions of energy that affect Earth in different ways. While solar flares release radiation, CMEs oust huge measures of solar particles into space. These phenomena can enhance auroras but also present critical dangers to Earth's technology and infrastructure. The sun's behavior is a fascinating interplay of physics and natural phenomena, influencing not only our solar system but also life on Earth. Understanding the intricacies of solar activity is crucial, especially as we continue to rely on technology that can be affected by solar events. The sun generates energy through nuclear fusion, converting hydrogen into helium and releasing vast amounts of energy in the process. This energy travels through the various layers of the sun, eventually reaching the surface and radiating into space. Solar activity can manifest in many forms, including sunspots, solar flares, and coronal mass ejections. Sunspots are cooler regions on the sun's surface caused by magnetic activity, appearing as dark spots. These fluctuations in solar activity follow an approximately 11-year cycle, known as the solar cycle, where periods of high activity, solar maximum, are followed by calmer periods, solar minimum. During solar maximum, the number of sunspots increases, leading to more frequent solar flares and CMEs. Solar flares are sudden bursts of energy that release radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These intense outbursts can affect radio communications and even create problems for astronauts in space. CMEs, on the other hand, are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. When directed toward Earth, these ejections can cause geomagnetic storms that disturb the planet's magnetic field, leading to beautiful auroras but also potential disruptions to technology. The impacts of solar activity are not limited to space. They extend to Earth's atmosphere and surface. Studies suggest that variations in solar radiation can influence climate patterns, possibly contributing to weather anomalies. Increased solar activity can also lead to atmospheric warming, which is an essential factor in discussions about climate change. Moreover, the potential for technological disruption due to solar storms cannot be underestimated. A severe geomagnetic storm has the potential to damage electrical grids, disrupt satellite operations, and affect navigation systems. Preparing for such events involves monitoring solar activity and developing strategies to mitigate their impacts on infrastructure. Scientists continue to study the sun's magnetic field and its cycles to better predict when significant solar events may occur. This research involves a combination of ground-based and space-based observatories that track sunspots, measure magnetic fields, and analyze solar wind. With advancing technology, our ability to predict solar activity improves, which is vital for safeguarding our technological systems and ensuring the safety of astronauts. As we learn more about the sun, its influence on Earth becomes increasingly clear. From the stunning displays of auroras to the potential challenges posed by solar storms, the sun remains a powerful force in our solar system. Understanding its cycles and behaviors not only enriches our knowledge of astronomy but also enhances our preparedness for the impacts of solar activity on modern life.